Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 482, Laser Plasma Interactions. It is the 9th lecture of this course, and today we'll be discussing the analytic solution of the electromagnetic waves that propagates through a plasma having a density gradient. We will take the simplest version of the density gradient, that is, the density varies linearly with plasma, or we can say the plasma thickness. First, I will give the learning objective. In this part of the course, we are discussing how the propagation of the electromagnetic wave modifies due to the presence of plasma. And today we are talking about the density gradient aspects that will modify the propagation of the electromagnetic wave, or we can say the laser. We are following the book The Physics of Laser Plasma Interaction by Williams L. Kruer. In this lecture, I have taken some of the illustrations from this book. If you remember, in the last few lectures, we have discussed the propagation of electromagnetic wave, and we have discussed the solution of the various aspects of the wave propagation in plasma, and one was the WKB solution. That was the approximate solution that we have discussed. So it provides a very intuitive way to describe the wave propagation. In such way, the wave is assigned with a wave vector and group velocity, which are defined via the local dispersion relation. The amplitude and phase of the wave are related by these locally defined characteristics in a physically obvious way. We have discussed the limitations of the WKB solutions. That is, strictly speaking, the approximation is valid only for very gentle density gradient, and in particular breaks down near the cutoff, or we can say the reflection point. We'll see how the analytical solution agrees with the WKB approximation for weakly gradient situations. Hence, it is important to complement the WKB solution with a more complete solution of the wave propagation, that is the analytic solution that we will be discussing here. Fortunately, an exact solution can readily be obtained for a plasma with a linear variation in density. As I told you that we'll be discussing only with situations where the plasma density is varying as we are moving more and more inside the plasma. So we can say that the density is linearly changes with plasma. So if you remember, we have considered a plane wave electromagnetic wave normally incident on a inhomogeneous plasma slab and allow variations in the z direction. That is, we are considering inhomogeneous plasma slab, and that gradient lies in the z direction. So we have developed this wave equation in the 7th lecture for a homogeneous plasma, and we have obtained the wave solution and the dispersion relations. But since now the plasma is having density gradient, so the plasma dielectric function is now depends upon the incident wave frequency, or we can say the laser frequency, and also it depends upon the z direction over which the plasma density is increasing. So keeping all the things same with the previous lecture, so we are taking the plasma vacuum interface is at z is equal to 0, but the plasma density profile is given by this density gradient equation, that is the density depends upon the z coordinate and it increases with z, where this RC is the critical density. Now if we want to use this density expression in the dielectric function, so we have the plasma dielectric function in terms of the density given by these expressions. You already know this. So if we use this density profile which linearly increases with z, and the plasma vacuum interface lies at z is equal to 0. So this differential equation for which we are looking for an analytical solution, that is this equation will give us the wave propagations of the electromagnetic wave in a plasma which is inhomogeneous. So we need to solve this equation for a density profile given by this. So if we use this plasma dielectric function, the density over here, so that this equation will take the form this one. So now this term is actually the plasma dielectric function. So we need to solve this equation. So for that we need to change this variable z with a dimensionless quantity defined by xi. We will see this change will give us a more control in order to check these solution or these electric field, and in the next lecture the magnetic field at different situation. For example, this will give us a nice control of the reflection point and the plasma vacuum interface. You will see that in a minute. But if we transform this equation from z to xi, so that the above equation, which is the same equation for which we are trying to find out the solution in order to have these profiles for the electromagnetic waves. So this equation, the above equation takes this form by transforming z to the xi. So this is known as the Stokes differential equation, for which the solution is given by the Airy functions. So this is an equation known as the Stokes equation, and this have this solution, that is the solution will be the E which depends upon the xi, which have these z dependence. So that we have the Airy functions ai and bi, these solutions. So we'll try to find out these coefficient a and b by matching the boundary conditions. So we will try to first take a more physical solution from this equation, and then we'll be going towards the properties of the electromagnetic waves, or we can say the laser wave that propagates through plasma. So the a and b are the coefficient that we will be determining. Now first we want to see and discuss this solution, that is the outcome of the Stokes differential equation, for which the profile of these ai and bi given by these profiles, such that the solid line is the profile of ai, which depends upon xi, and this is the rate of change, and this is the bi. As I told you, we need to make this solution more physical for our situation. So for that we have the density profile given by this, and the xi over which this is a coordinate, or we can say the independent axis given by this. So from the density expression here and from the xi, which is the independent parameters, now this expression give us the plasma vacuum interface at z is equal to 0, and also this will give us the place where the density reduces to critical density, and that will be when hexa E equal to 0. So once the hexa E equal to 0, Z is not equal to 0, so that is that particular point. So from this density and this hexa equation, one can get that as the hexa E equal to 0, so hexa E equal to 0 for AI over here, and hexa E equal to 0 for BI equal to here. So at hexa E equal to 0, the density is equal to the critical density. And at hexa equal to, say, at hexa equal to, let's say, in another words, Z is equal to 0. If you solve this, Z is equal to 0, so that will be the other point. So we are discussing this solution at plasma vacuum interface, that will be Z is equal to 0. And the other point is when hexa E equal to 0. So we have discussed the solution when hexa E equal to 0, so that is the critical density, and that is the we can say the point of reflection. And once Z is equal to 0, so if we solve here, this hexa E will equal to minus then omega L over C to the power 2 over 3. If you solve this, you will get for Z is equal to 0. So that will be the plasma vacuum interface. So that we have the density profiles given by these three limits: the vacuum, the plasma, and the critical surface. So one can say that by discussing the profile of the density at the plasma vacuum interface, and also the reflection point, or we can say when the density is equal to the critical density, one can say that the electromagnetic wave, for which this is the profile of that electromagnetic wave inside the plasma, cannot propagate when the density is, we can say this N is greater than the critical density, or in another word, equivalently this hexa E greater than 0, that is hexa E greater than 0 is this side for BI, and this side for AI, the Airy functions. Since the Airy functions, by looking at these profiles, the BI diverges for hexa E goes to infinity, right? It goes to diverges for hexa E tends to infinity. So one has to exclude this this portion from the solution, that is this B coefficient is equal to 0 in the solution. Therefore the electric field profile is given by only the AI solutions inside the plasma. So for that we need to we have just taken the solution of the Stokes differential equation, and then using the plasma vacuum interface and the reflection point, we need to take the solution as E, which depends upon hexa E equal to A times AI of hexa E, so that is B equal to 0 for physically valid solutions. So now, how one can obtain these coefficients? So it is assumed that before going towards the solutions of these coefficients, we need to make another assumption, and that is already there. It is assumed that the dimension of the plasma L from the vacuum to the critical surface, if you remember, we have discussed Z is equal to 0 is the point where the laser incidence on the plasma, it is that interface to that critical surface is large compared to the electromagnetic wavelength, that is the lambda associated with the electromagnetic wave that is incident on the plasma is large, that is this L is large compared to the lambda associated with the electromagnetic wave. So on the other hand, if we say that this L is of the order of the product of the laser time duration and the plasma expansion plasma velocity, that is this L, which is dimension of the plasma, has to be greater than the wavelength, or we can say in terms of time we can calculate this thing. So that is why this approximation in this section we see here is not relevant for the femtosecond lasers. So at the end we have an assignment that we will be calculating these scales for a particular situations. So the assumption is for the wave propagation through the plasma, that this L, which is the dimension of the plasma, has to be small compared to the length scale, or we can say the wavelength associated with the electromagnetic waves. Now the plasma vacuum interface is at hexa-e, which you can work out from the previous slide. Therefore we can use the asymptotic expansion of the Airy function given by this expression. Now in order to describe the electric field near the plasma vacuum interface, therefore the electric field at Z is equal to 0 from the plasma side can be approximated by these expressions. So we are trying to find out the solution of the electromagnetic wave, or we can say the analytical solution, and we are taking the Airy functions, and for this we are trying to find out the electric field on either side of the interface. So looking from the vacuum side, one has at Z is equal to 0 the incident laser electric field and the reflected part, so that the plasma side and the vacuum side at Z is equal to 0. So that if this solution can be expressed in this form as well. So if we equate the two solutions, that is the solutions are continuous across that plasma vacuum interface, so that the continuity of the two solution on either side will give us the coefficient A. So that the requirement that the solution is continuous at the plasma vacuum interface will give us this A and also the phase part. So if you remember, that was our solution of the differential equation, for which we have discussed that for physically valid solution this B coefficient has to be 0, so the solution is E is equal to A times the Airy functions. So as I told you, these coefficient A and B is also already 0, so the A can be obtained by equating the two solutions at the boundary, so that we'll be getting these A and phi. So if we use these A, phi in the solution itself, so that this hexa-e will be equal to the A times the Airy function. So this is the A and this is that Airy function. Also if you go towards the graph for the AI solution, the Airy function, so that is maximum at hexa-e equal to -1, so that you can verify it from the figure, that is this has a maximum value at -1, so that the ratio between the maximum value of the electric field in the plasma and the laser electric field in the vacuum is given by this thing, so that the E maximum over E laser can be approximately equal to this thing. As I told you, we'll be talking about these scales in a minute. Now how one can obtain these values? So for that you need to solve this assignment. For example, for a laser produced plasma with a dimension L equal to 100 micrometer. So we can say this is the dimension or the thickness of the plasma, for which a laser wavelength of 1 micrometer. That is, if you see, as I told you, for the solution that we are discussing, L has to be larger than the lambda associated with the laser. So 100 is far greater than 1 micrometer. So you need to use these scales in order to find out the ratio of the maximum field in a plasma to the laser by this expression. So if you use here these number in using this equation, you need to verify that this ratio E maximum over EL is approximately equal to 5.57 because this is the ratio. So this number you need to verify this for a situation where lambda is 1 micrometer and L is 100 micrometer. Now in the coming lecture we'll be discussing the same lecture, but we'll be talking about the magnetic field profile of the laser. We have discussed the E part and now we'll be left with the B part of the wave propagation. So with this, I thank you for your time.